Math 5500. Going to switch gears, new stuff here. The last video was just pumping the brakes and uh, revisiting a couple of things. I want to switch gears here to take a look at the estimation of error term variance, sigma squared. And you'll notice on the right side I have R that's visible, and I have a data set. There's some stuff, looks like a percentage score in the year, so I have no idea. But I do know that this is the ACT score, and this is the first year college GPA. Now you can see that the length, 705, so we have a sample size of 705. We have a really, really large data set. So I want to use this data set to bounce off some ideas. Now, the goal here is to learn more about the variability of the probability distribution of Y. And we know from undergraduate statistics that, in a single variance setting, that the variance the sample variance is an unbiased estimator of the population variance. However, we know that that the sample standard deviation is a biased estimator of the population standard deviation. So just keep that on the back burner. All right, so let's look at a few things. So at a particular level of x, we have 3 points that emerge as interesting. The first thing we have is the observed y, so I would call this the y sub I. The next thing, if assuming we have a min y and a max y, which is a reasonable assumption, right? If we have a mean, it would be somewhere around the center of that. So this would be y bar, and of course this point right here would be the predicted value y hat sub I. Now, the first thing I want to do, well, obviously you have a really, really dull data set if you only have one observation. So we have other, x's, and of course create our model. And as long, with other x's, we have other y sub i's too. So the first thing I want to do is I just want to focus on the y sub i's, okay? And I want to look at the deviation of the y's. Now, not getting to the good stuff yet, not looking at the deviations of the errors. I just want to look at the deviations of the y values. So the y values here will be 0.98, 1.13, 1.25. I just want to look at the deviations here. So it may be interesting to examine what is going on with y sub I minus y bar squared, so the deviations of y from the mean. And we'll give this a name, the sum of squares. Now, what we can do with this, and what we do with this, is we create an estimate, which I will call the sum of squares, divided by the degrees of freedom. So the sum of squares is, again, the sum from I equal 1 to n. Please forgive me for no subscripts on the summation. So again, sum of squares is the deviation squared of y over the degrees of freedom. And the degrees of freedom in this situation will be n minus 1. We lose a degree of freedom because we have used y bar, the sample mean, to estimate the population mean. So once we divide by, when we take the sum of squares divided by the degrees of freedom, then we call this the mean square. And it would be very, very, very easy to calculate the mean square using R. Now, from before, we know that the variance of each y sub I is sigma squared, which is the variance of each e sub I. So in other words, we're going to switch our attention because we know that each one of these y sub i's comes from a different distribution with a different mean, right? So if I, for example, choose an x sub j out here and focus on this distribution versus this distribution, well, they're different distributions because they come from different means. So the deviations of a y sub I must be calculated around its own mean, y hat sub I, the predicted value. So put x sub I in our model, come up here and predict. This is the expected value, the mean of that distribution. But our focus is what's going on with this variance. But anyway, we know that the deviations of a y sub I must be calculated around its own mean. So bring some new stuff. So we know that the error, therefore, is defined by being the observed minus the predicted. So we can have what's called the sum of square error, which is SSE, which is the same thing as the sum of the error squared. So as before, this with degrees of freedom, we have two estimates that were made. So we lose 2 degrees of freedom. Now, what two estimates were made? Well, clearly we had to estimate beta 0 and beta 1 with B0 and B1. Otherwise, we couldn't have made this predicted value. So our degrees of freedom here changes. And we create what's called the mean square error. Which is just MSE, which is nothing more than the sum of the squares error divided by the degrees of freedom. So guys, when we take a sum of square and divide it by the degrees of freedom, it becomes the mean square. So the sum of squares for the error divided by its degrees of freedom becomes the mean square for the mean square error. So for the most part, this is the sum of the errors squared over n minus 2. So sigma is obviously estimated by S, which would be the square root of the mean square error. So let's calculate So what are we doing? Predicting from ACT. So first thing we want to do is get our model. And predict GPA from ACT. And we get our model. Okay. So essentially the sum of squares error is just the sum of the errors. So what I want to do is I want to create error. And I want to take the y values, which would be GPA. Minus the fitted GPA. sure I got my parentheses right. Yeah. Anyway, what did I do wrong here? Oh, I had a bozo moment. So then I want to sum the errors and divide by length of GPA minus 2. So from this I get the sum of squared error term. Now, if I want to take the square root of that, then I get the standard deviation of the error terms. So, easy stuff, right? Now, I'm distracted because it looks like the UPS guy's here. So sorry if I seem distracted. It's because I am. All right, gang. So, by the way, it's very likely that the doorbell's getting ready to ring. So we have 3 parameters. So beta 0 is predicted by beta 0 hat or B0, beta 1, beta 1 hat or B1. And of course, the sigma squared is by sigma squared hat. I gave you this in a previous over n. But, huge but, sigma squared is biased. So we use the unbiased estimator. The mean square error, which is what we just covered. Now we expect these things to vary a little bit, but I will tell you that the mean square error is going to be very, very, very close to what we talked about before. And actually I'm probably not going to get this right, but they say that the mean square error, if you multiply by n over n minus 2, times the predicted value, I believe this is it right here, I know this is it, when n is large, that will make the two extremely close. But in general, the mean square error and the predicted value for the variance will be different. So again, because this is an unbiased estimator, we refer to the MSE, mean square error, that I just presented to you. All right. Well, I'll tell you what, I think this is a really good place to stop. Okay, I'm hesitating. I want to show you guys something, but it's just not yet the time. So I'll tell you what, let's just stop the video here. All right, take care.